So just in anticipation of issues that you may have with setting up the software, if you know somebody who's good at Windows, you should just ask them to help you. But the command prompt is just called command prompt, but in different computers, it may be in different places. But usually it's found in the system folder. But you don't necessarily need to go here to get it, because you could probably get it from the list of installed programs with System 32. And then the file name is command.exe. And basically, when you find it, you need to right-click on it, send to desktop. Okay? Then it'll be there. Then put the programs. The programs are now on the website. Either in an existing folder where you keep your X-ray programs, or you can create a new folder, a new subdirectory to put them in. Like, for example, you could put them in something that you call SXTL. Just put them in there. So you'd have to create this file name and put them in that folder. And then in order to access them, they need to be in what's called the path. And you set the path. Sorry about all the technicalities, but you set the path in the environment variables. And you can search for that to find it. It's usually very easy to find it if you go to the control panel. First, go to control panel, find environment variables. And you need to edit the path so that it knows where your programs are stored. So there's going to be a value called path. And these are the user variables now. There's two different kinds, system and user. You probably already have the number of items in the path. They're separated by a semicolon. So, there's a semicolon, a bunch more items. Finally, at the end, you're going to add the path to this folder, or whatever folder you've chosen to put them in. Make sure that you have it there. So it'll be something like, I think this will work, just C \SXTL. So you're just going to add that to the existing paths by adding a semicolon and then the location. Okay? So you edit a path and add that. I think that's going to work. If you guys find that it doesn't work, maybe you can figure out why not. So sorry that this is so technical. There's one other thing, though, that I recommend, and that is that you don't hide file extensions. For some crazy reason, the default in Windows is to hide file extensions. But what we don't want to hide file extensions. We want to see them, right? We want to see if it's HKL or INS or RES, all the file extensions. We should be able to see them. So the place where you can go to Control Panel again, and under Files and Folder Types or something like that, you can search for Show or Hide File Extensions. And it'll say Show or Hide, what it says, Show or Hide File Extensions. And you want to uncheck the box that says hide. Don't hide, okay? The one that says hide. Whatever it says. So that's all. Just if you can just do those things, I think we'll be smooth sailing after that. I hope so. If you're using Windows 7 does this really easily. to tell you the truth, I think it's harder to do in Windows 10 because they start taking away, your control of the computer and forcing you to do it the way they want to do it, like forcing you to run Edge instead of Google or something like that. It's terrible. I think I'm going to get rid of this laptop. I don't like Windows 10. So, okay. So play around with that a little bit, and then be sure and bring your computer next time. We'll see if we can go through some easy refinements maybe, and then maybe some more difficult ones. We'll have to pick some out for you. But just as a preview, some of the things that you encounter that are the things that you're going to hate are disorder and twins. And I think disorder is more common than twinning, actually. So let me just give you some examples and then some ways that you can deal with disorder. Over the years, I've become very good at it, but it's very boring to explain it to somebody. So I'm trying to not make it too lengthy. But if you have an individual structure you want me to look at, I can also help you with that. So occupational disorder is very common when you have, let's say, high symmetry and this atoms can't decide whether to go on the top side or the bottom side. So this was just a very simple example where you have a iron porphyrin and it has a water in the axial site, but it can be, see, because there's a center of inversion here on the iron, the water can be at either side. But it can't be simultaneously at both sides. However, by the symmetry operations, it's going to put it on both sides. So the only way around that is to set the oxygen and its two hydrogens to half occupancy so that you're not overstating what is there. So just in the atom list, you set site occupation factor 10.5 instead of 11.0. And you have to personally do that because the software won't do it for you. You have to set the occupation to what you know is reasonable, and then it will be fine, and thermal parameter will look good, and it will converge, and it will be very good. So that's just a really simple example, and not the worst kind of disorder that you encounter. Here's another common one, though. A BF4 group. You can see it sort of inverts through itself to form a second BF4 group, and it just has a couple of common, well, the common atoms are the ones I've labeled F1, F2, and F3. So those are all at full occupancy, but the other ones are at half occupancy, the F4 and F4b and B1b. Why does nature do that? I think it does it because when you have this kind of disorder, it takes up a void space in the crystal. And there's sort of a saying that nature abhors a void. That means that really it likes to fill the space. And sure, you think about it, you have more intermolecular interactions, which are favorable energetically. So if there's enough space, it may just do to the disorder. If there's less space, maybe it won't. But you could see BF4 groups in many different ways disordering. This is just one way. My favorite examples, of course, are with fullerenes. So here's one which is illustrating the rotational disorder that's so common with fullerenes. And at high temperature, it's worse than that. At 104 Kelvin, it orients in just two different ways. And there's 4 benzene groups, but one of the benzene groups is rotationally disordered also. You can see how this one here is in 2 different positions, looking kind of like a flower or something. But for some reason, these 3 are perfectly ordered. And the fullerene itself has 2 positions at this temperature. However, what happens if you raise the temperature, it becomes really awful. There's like at least 4 different orientations of the fullerene. And I just wrote high T, but I think that's probably just a little bit above that other temperature, like 120 or 180 degrees. And here you see the disorder in that benzene also. Now, the interesting thing is, you go below 104 degrees, it undergoes an ordering transition and becomes perfectly ordered, but in order to do that, it has to double the unit cell. So it's the c-axis. Other axes are the same, but the c-axis doubles to accommodate the phase transition. And so you get this molecule, different orientations. And strangely enough, this one benzene, though, doesn't order. It stays disordered at the low temperature. Ordering transitions occur frequently at low temperature. Another reason to use low temperature, although it often is accompanied by twinning when the order transition occurs. So you have to know how to deal with the twinning. But since the molecules are ordered at low temperature, the twinning is usually not a problem. It's just a question of finding the twin law, which relates one orientation to the other. Again, really not too difficult, and I maybe have a chance to show you how to do that. Okay, so there's that kind of disorder. Perchlorates are notorious for being disordered, but sometimes they aren't disordered. So here's a structure with two perchlorate sides. This one's fine, that one's disordered. Go figure. Then there's an acetonitrile, which is fine. But in order to publish a structure like this, you really have to deal with its disorder. You have to model it some way. And I'm going to tell you a really cool way of doing that. Okay, and this is extremely common, toluene disorder. Sometimes they're so overlapping with one another, like this atom and this atom are so overlapping that you can't even tell what's going on. But in this case, they were just a little twisted, and it was pretty easy to sort out two different molecules, but not at, each is at a lower than full occupancy. Okay, so this was a fun project that I visited Malaysia for a while, and one of the folks there had published this paper, well, several of them. These are all people at the University of Malaya. And they describe, this was in Acticrist E. It was just a brief structural report, not a big deal, but the molecule, the title compound is whole molecule disordered, about an axis that runs approximately along the length of the molecule. The occupancy of the two disordered components was set as exactly 0.5. And I believe that was an arbitrary choice of 0.5. And then there is this hydrogen bond. Well, I looked at that and I knew that I could model that disorder better than they did in the paper. It was really not a very good job, although I don't think I ever told them. But with my student at the time, who is not on that paper, Hamid Khaledi, though, who I worked with, we went through it and modeled it better. And so what you have is this molecule right here. That's sort of the main molecule. And then you can slap another molecule sort of on top of it without changing the space that it occupies. You just flip it over. Okay. So molecule 2 is just flipped over from the other one. And then you can kind of imagine how they would superimpose. And the way to deal with this is to use the major one, which it actually was more than 50%, as a model for the second one, and then treat that model as a rigid group and superimpose it using something called frag, which is a part of the Shellix software. So when you do that, you can see how they, they're very similar in the space that they take up. But when you first look at that, of course, in a difference map, you go, wow, what is that? So we were able to successfully model that and get a very low R value compared to the publication. But anyway, it was just an exercise. Now, whole molecule disorder is much rarer than other kinds of disorder, like with solvents and that kind of thing. But it does occur. In fact, the C60 example I showed you was whole molecule disorder. I took a whole ball of C60 from another structure and pasted it in as a rigid group to model the two on top of each other. Yes. Back. Mm-hmm.
If the old molecules is a primary structure, then we can, by giving the what command, is it helpful to solve the structure, or in which way you are giving it? Just like that, you are showing a.
No, well, that's the end result, but the part commands are just part of doing it correctly. There's a few other commands that you need, and I'll explain those. No, in my mind, the part command is not enough, and I think in the original paper, they had some restraints built in so that it would behave better, but it wasn't nearly as clean as this. This is actually very clean. You could take part one and look at it, and you see, I mean, it looks like part two. So it was more well behaved than the original publication. But you need some affixes and things like that too. So that's another use of the affix command. This was another interesting case of disorder that created a lot of controversy back in the 1990s. In fact, this guy's career was really based originally on this question, do bond stretch isomers really exist? So he had this transition metal compound. Here, it's depicted here, and he had two different colors, a blue and a green. And at the time, he thought the two colors were due to cis and trans isomerization. But the funny thing was that the molybdenum oxygen distance in the blue crystals was quite different from the molybdenum oxygen distance in the green crystals. And some people said, well, that just shows you can have bond stretch isomerism. But he didn't really believe that, and I didn't either. And what he did was he got the crystals and sent them around the world to his friends and said, would you redetermine this structure for me? And I was one of the people who looked at the crystal structure. And they weren't cis and trans. They were the same. They were both cis isomers, as shown here. And so what was happening was, I think you can well imagine that the chlorine and the oxygen were just sharing the same positions, but in different ratios in the two crystals. Okay? So it wasn't a bond stretch isomerism, but disorder that was causing that. So the longer the bond, the more chlorine there was in this side. The shorter the bond, more chlorine in this side. I mean, it's a clear case of disorder, and pretty easy to describe once we figured it out. And how do you do the refinement then? You know what, by the sum of the covalent radii, or from looking at the CSD, what the distances should be. So you fix them, you restrain them to those distances in the refinement. And if your assumption is correct, that refinement will be well behaved and our value goes down and everything looks great. So that was actually what was going on. So here's some more about it. So it's just the percent of chloride. So he was just a young assistant professor at the time. He became one of the editors of inorganic chemistry, ultimately, a very famous inorganic chemist. But that was fun in those days. Okay, now I'm going to talk about frag. This is pretty advanced stuff, and bear with me because it's extremely powerful. And maybe the first time you try this, you won't get it right, but you can always ask me, and I can help you. So one of the ways you use it is this whole molecule disorder idea. But you can also use it for disordered solvents, disordered parts of molecules. It cuts down the number of parameters that you would need to use otherwise, because you're using a rigid group, and a rigid group basically only has 6 parameters to it. Translation along the 3 directions and rotation around the 3 directions, 6 parameters. Whereas if you have lots and lots of atoms, then each atom contributes usually a minimum of 4 parameters, and so on. So you don't make any extra parameters for a rigid group. It can either be riding on some other atom, like rotating around a bond, or it can be freely rotating in the structure. Those are 2 different ways. And yeah, so we do this to avoid unreasonable geometry. And sometimes it's just done because it's a part of the structure you can't model easily. So that's why. So some of the rigid groups that are good are things like these solvent molecules, which have very rigid geometries. And we encounter these so often. So by rigid, I mean that all of the 1, 2, and 1, 3 distances and torsion angles are known, predictable, not going to change. But something like ethanol, it can have more than one conformation. You know, you can have a zigzag conformation or a non-zigzag conformation. So I don't count that as rigid, although the zigzag is more common. So sometimes you can use the zigzag. And of course, these kinds of big groups, carburenes, C60, C70, they're rigid groups too. So some of these rigid groups are actually built into the ShellX package. I don't know if you realize that the benzene molecule is built in. Have you ever tried to use that? It's another affix 66, and pastes in an ideal benzene ring. So it's built into the software. Also, affix 56 pastes in a CP group, cyclopentadiene. And this is a more advanced way to refine a cyclopentadiene group. It allows it to shrink or expand. And affix 33 pastes in an ideal methyl group that rides on the previous atom. We talked about that before. But in all cases, affix 0 ends the rigid group. So what do you need to do? Essentially, you only need to have 3 atoms, but they should not be coplanar. But 3 atoms that are not coplanar to define the initial orientation. And then after that, everything follows, you'll see. Okay, so let's look at the benzene case. You have a benzene, and you can clearly see, you think, 3 atoms that you feel confident about. They could be either bonded to one another or they could be spaced, but you're pretty sure it's a benzene, and you have 3 atoms you're pretty sure about. So let's say you've numbered your benzene ring 1, 2, 3, 4, 5, 6, and atom 1 you have positions for, atom 4 you have positions for, and atom 6, at least approximate positions. Then these, 2, 3, and 5, you're not so sure about. So you don't need them. You only need 3. And because affix 66 accepts coplanar atoms. So you just put these in with 0, 0, 0 coordinates, the other ones that you're not so sure about. And in your ins file, you're just going to put affix 66, and then these 6 atoms with 3 of them known, and affix 0. At this stage, I wouldn't worry about hydrogen positions, just worry about the carbon positions. Then you do some refinement, and the res file has filled that all in and made you a benzene. The second 6 on the affix 66 is referring to this particular group. The first 6 refers to the fact that it's freely refining. So if it were, no, did I say that backwards? It might be the second 6. I'm not sure. If there's a 3 there, though, it's riding. And then you're talking about a phenyl ring, which is not quite as symmetrical as a benzene, right? If it's attached to something, or say a pyridine or something like that. So it's not exactly the same as a benzene, and you want to probably use more realistic bond distances for that. This assumes all the bonds are the same, and that it's an ideal 120-degree molecule. Okay. So, but that is built in, and you can use that. Now, if it's one that's not built in, another approach is to use this defix. It stands for distance fix. And it doesn't involve angles, it only involves distances. So you have to define, like in a BF4 group, you have to define the BF bonds and the FF bonds. Because if you don't define the FF bonds, you're not fixing the angles, right? So by geometry, it's pretty easy. If you assume tetrahedral geometry, that whatever the BF distance is, the FF distance is 1.633 times the BF distance. You can just do that by regular geometry, figure that out. So there's really only one variable here. And this would be, say, the way you would set it up. All of the BF distances in pairs, and then all of the FF distances in pairs. Okay? And then on the F bar line in your input, you need to have, after the scale is always there, so the first term is always scale. The second term, you put in a starting value for 21, which is called a free variable. It's just George Sheldrick's way of naming it. The 1 refers to being at full occupancy, and the 2 refers to the position in the F bar line. If you have additional such things in your structure, you would have additional things here after that, like 31, 41, and so on. Okay, so this is just a starting value, and it's a parameter, so it will refine. And again, it's just one parameter, because this one is related to that one by this factor of 1.633. Okay. So that gives a really nice result, and that's not a bad way to do a rigid group, actually. But this is a simple case. Some rigid groups are not so simple, like the whole molecule disorder that I showed you. You can take the same approach for PF6, anemone F6, all kinds of things, ASF6. Anything that's octahedral or tetrahedral works very well. Okay, so what about a general fragment, something not so simple? So this is what you do. Now, this is the hard part. And maybe I should show you a live explanation of this. But say like that example I showed you with the structure that had 1 good perchlorate and 1 bad perchlorate. You could take the good perchlorate, write it in as a rigid group, and paste it in for the other one that was disordered. That would work too. That would be using maybe the same command, which is another command, SAME, or you could use it as a fragment. Okay? I don't want to go too fast here. If you have seen this molecule before, you can just take it, and it was good before, you can use it. Or you can use the CSD to find something that's similar. You could say use that BF4 that I just showed you, that it's going to turn out pretty nice, and you could use that as your model. So you're looking for something that's an idealized rigid group that you can use to paste in and then map that to a poorly described group. This was in one of the things that we uploaded, a website where you can pick up some computationally determined idealized geometries. Now those are not maybe exactly the X-ray values that you expect, because sometimes X-ray values shorten bonds over what they should be. But it's a good start. This library was created by Ilya Guzai, who's the crystallographer at the University of Wisconsin. And he's generously kept that on his website for us to look up these molecules. It's quite a long list, actually. Okay, so what are you going to do? Now, here you have what I showed you before, a BF4 group. And it turned out that those, what I called 21 before, they ended up refining to 1.37 for BF and 2.237 for FF. And I had a set of coordinates for those atoms. So now what do you do? Okay. If it's in a different molecule, a different structure, not the same structure, the easiest way to do it is to convert that to Cartesian coordinates, because it's in crystallographic coordinates, and in another structure, it's not going to have the same coordinates. But the Cartesian coordinates can be read in. So you create a fragment, and then you paste it in. And if you use the Cartesian coordinates, you can just put them at the beginning of your atom list, for example. with frag in front of the first atom of the list. Usually I use 17, but it has to be more than 17 or equal to 17. And this is only if you're using the existing ABC. The default is actually this, which is Cartesian. So you don't need to actually put in the rest of this here. All you need to write is frag 17. Then how do you get the Cartesian coordinates? Well, I think XP does a nice job, because XP you can just say orth and then give a file name like c60.ort, and that's Cartesian coordinates. So ORTH in XP gives Cartesian coordinates. I'm not sure what WinGX does about it, but it's probably in there somewhere. Okay, so if you're using the crystallographic coordinates, you have to put in ABC, alpha, beta, gamma. Okay, so here's an example of a 5-membered ring. And these are Cartesian coordinates. You can usually spot them because the first one is just 0, 0, 0. So these are Cartesian. Yes, it has to just appear before this fitting process. I usually just put them at the top somewhere. It starts with frag 17, it ends with f end, frag end. Okay, so bear with me. So here's the beginning. You have this fragment, and then you have this group of atoms, 5 atoms, that are not well behaved, but we think that they fit this, they should fit it. You start this group with 176. The 17 means that 17. The 6 means freely rotating. And you end it with affix 0. And then after refining, or not, actually in this case you don't need to refine, you could just say LS0 to see if it is reasonable. And it generates the rest of the coordinates. Now I find that the most common error here is to not have them numbered in the same order. So it's a really good idea to sketch the numbering order for this fragment and the numbering order for your molecule, and make sure that they go in the same direction. It's not reversed or, skipping. They should be numbered in the same order. And to ensure that, it's a good idea to just put the first 3 at the front, but you don't have to, as long as they're in the same order. Okay, so going back to this whole molecule disorder, we did this already. But the reason that worked was that the molecule is a rigid molecule. And there were some Q peaks. I mean, this structure, the main molecule showed up pretty good. There were quite a few Q peaks that were more than 1. And the Q peaks really looked like they were trying to be another molecule. You see what I mean? And sure enough, we were able to fit the rigid group to that with some fiddling. And it was a large rigid group, a lot of atoms in the fragment. So again, the first 3 atoms are the only ones that really matter. You put them at the beginning of the set. Make sure they're exactly in the same order. One maps onto the other. Somewhat like this. So I just picked those 3, and all the rest were zeros. But it had exactly the same number of atoms as in the other molecule. And then looked at it, looked good. And did some cycles of refinement. Okay, here's the end result now. This is a different sketch of it. But the R value dropped, okay, not a huge amount, 0.03 to 0.02. But you see it in the difference map. Before adding the second molecule, the biggest Q peak was 1.16, and afterwards 0.25. So we had taken care of all of those Qs at least, which was it was satisfying to see that. Okay, so more about disorder later. But what about twins? There's a lot of different ways to handle twins, and if you can get away with not having a twin, that's my best advice. If you think you can find a crystal that's not twinned among the batch that you have, go for it, because this takes a lot of extra time. There's several different kinds of twinning. Merohedral twinning is this definition. The twin law is a symmetry operation of the crystal system, and superposition is exact. So essentially what you have is two unit cells that are oriented in some way, like versus, say, a twofold axis or some other way, but causing all of the spots to be superimposed. And that's very, very hard to sort out. Mostly you only see this in the very high symmetry space groups like hexagonal and cubic, and mostly you only see it in the cases of simple inorganic molecules that don't contain carbon and oxygen, but just metals. So that's rare for small molecule crystallographers, and if you do have that, good luck. Now, pseudomerohedral are lower symmetry space groups typically, but you still have some overlapping. That's why it's called pseudomerohedral. So you have to deal with reflections that are actually composite reflections coming from two different twins, and some that are not. And the way you spot that in the diffraction pattern is you have things that are too close together, knowing, say, your approximate cell dimensions. So eventually you get to the point where you can look at a diffraction pattern and say, oh, that one is a twin. So in solving the structure, you may find that it has a higher symmetry than actually exists. For example, if it's monoclinic and the beta angle is close to 90, you may think that it's orthorhombic, just like that example I showed you yesterday, which wasn't a twin actually, but it could have been. So you have to consider that. If you're getting an angle that's not exactly 90 degrees, or not within, say, 0.5% of 90 degrees, you might be observing a twin in that case. But that actually can be refined well by introducing a twin law, which we call a twin law, which would just interchange. It would just reflect the structure through B. Anyway, there's some really good papers on this. Regina Herbst-Immer, who works with George Sheldrick, she worked with him as a grad student, and she's still working with him, has written these two papers, which I really admire. She figured out an awful lot of stuff. And the whole chapter in the Shellick's manual on twinning was written by her, too. So she'll give she gives some examples of twin laws that work in specific cases. And this is one of the cases that she talks about quite a bit. So what you have to do is put in a twin law that you can just write twin if it's simply inversion, but if it's not inversion, it's a twofold or something like that, more complicated, you need a law. So that means you're putting in 9 numbers that are a matrix. This program, Platon, which I hope I have time to show you a little bit about, will help you a great deal in figuring out twin laws. It figures them out for you. It's amazing. There's a couple of different kinds of HKLFs. You can use 4 or 5. Let me show you on the next slide, I think. No, not the next one. Come back to that. Here's the difference between HKLF4, which is what you normally use, and HKLF5. So HKLF4, as you probably realize, is the standard HKL. It has HKL intensity and sigma intensity. So just those 5 terms. If it's HKLF5, it contains a batch number, something called a batch number. And I think I have an example here, yeah. So here's HKLF5. HKL, intensity, sigma intensity, and then the batch numbers. So one way of managing twins is to use the HKLF5 file. But sometimes you can, if the second twin is minor, You can just get a good structure using the major component, and you don't have to use the minor one anyway. It just depends. So, okay, you have to do a lot of fiddling around. You can either deal with the twinning by the integration, or you can deal with it after the integration. And I can't give you a general rule, which is better. I mean, I end up trying just about everything when I have a twin, so try to avoid them. Let's go back. So indications of twinning. Again, if you have a polarizing filter on your microscope, you can usually see twinning because it'll not blink all at once. It blinks partially at one setting of the stage and then partially again at a different setting of the stage. But you should see it goes dark light, like every 880 degrees as you rotate. That said, a cubic crystal does not extinguish anyway, so, and neither does hexagonal if you're looking down the z-axis. Plates are often twinned, so expect it if you see a plate. Again, what I was saying, the diffraction pattern shows spots that seem to be too close together. You have difficulty indexing it. The R value seems to be too high, and a lot of times f-obs is greater than f-calc. But that can also happen for other reasons, so it doesn't necessarily mean you have twinning. If two axes are of similar length, you know, what's going on when a crystal grows is you have this nucleation site, and then the molecules come and settle down in their preferred orientation. But if two axes are the same length, they can start settling this way and this way, right? Because the length is pretty much the same. So sometimes that's a cause of twinning too. Yeah, monoclinic with beta near 90 degrees is a really common thing. If you have monoclinic with beta near 90 degrees, you should consider that it might be twinned. Okay, so for the strategy for data collection is high redundancy, as I spoke about before. So you may need to do some extra data collection. The third point is also important. If it seems like there's a lot of overlap in the spots, you can avoid some of that by moving the detector back to a longer distance away from the crystal. That spreads everything out more in reciprocal space, and it might be easier to reduce the data with the detector moved back and the spots further apart from each other. Because the problem comes in these composite reflections where you've got a contribution from each twin. Figuring out which belongs to which is sometimes difficult. It wouldn't even be a bad idea to sometimes just select P1 so that you don't have to make a decision at that time about what's the correct space group. You can just say, okay, it's triclinic. I'm going to collect everything I can. So the strategy also is a factor. Okay, then that, I showed that. Oh, that's all. Okay. So what have you observed? I want to hear your observations about disorder and twinning and, yeah. Cases where you found a better crystal by trying maybe 6 crystals and you finally found one that wasn't twinned, or you never could find one that wasn't twinned. Or what? Yes? AFIX 66 is designed specifically for benzene. No, frag is for whatever you define to be the rigid group. So you decide what the fragment is, and you put in the coordinates for it. So the AFIX 66, it's built in to the software for benzene. Okay, so SADI stands for same distance. Okay. Yeah, again, the first term is going to be standard deviation in the case of SADI. So you might say, okay, I want these to be equal to within 0.02 angstroms. And then you could put in, let's say you have a disordered dichloromethane, just for example. Maybe, C59, Cl1, C59, Cl2. And you don't, in the SADI command, you don't have to specify the distance. You're just saying, I want those to be equal. And so you could put as many as you want here, but they have to be in pairs. Okay. But the list can be very long. That's different from defix, where defix you have to specify the distance followed by this standard deviation, and then the pairs. And then there's one other constraint that you could use, or restraint, I guess is what he calls it, the same, which also works. It's a little tricky sometimes to apply. With same, you don't put in a preconceived distance. You're just requiring a sequence of atoms to be the same as another sequence of atoms. And the order in which you put things is pretty important. Let's just take a simple example. So you have a really nicely defined perchlorate. And then a bad perchlorate following that. So in here, you would put same Cl1 space greater than space O4. I'm sorry. Yeah. So all the atoms from Cl1 to O4 would be used to optimize these distances in the poorer perchlorate Cl2 to O8. It's basically considered a restraint, not a constraint. The defix is more of a constraint. It sometimes works. There is one problem though, that when you refine with the same command, it isn't saved for some reason. So you go back to your INS file and the same command is gone. And then there's a message that says, same must be entered again. So you have to remember where you put it in the file and put it back in. Yeah. If you need it again. It could be that you won't need it again because this has now been figured out and it's well behaved. But initially, it will optimize that geometry to match this one. Is that clear? Okay, yeah, good. Again, the order is very important. If these are not in the same order, then it won't work. So, I mean, perchlorate is not bad because it doesn't matter the order so much, but in some other molecules it will matter. And then you'll just mess it up completely if they're not in the right order. Okay? Yeah, go ahead. Okay, so EADP and ISOR. Okay, so ISOR is one way to take care of this complaint when you're doing refinement that such and such an atom is NPD, non-positive definite, right? So it means probably that the ellipsoid has a shape that's just so skewed that you end up dividing by 0 and the matrix becomes indeterminate. So non-positive definite. So it's usually because either you have too few data or you have a very skewed anisotropic thermal ellipsoid. If you use the ISOR command, it makes it more similar to an isotropic thermal ellipsoid. So you can just say ISOR. And then the default for that is maybe 0.02 or 0.01, I forget. But it's of the order of an isotropic thermal parameter. Yeah. So you can fiddle around with this. Say if you use 0.01, and then the bad atom, C52 or something like that. It won't make it completely isotropic, but less, the axes of the thermal ellipsoid will be less different. I mean, yeah. So it's again a restraint that's making it more approximately isotropic. Sometimes that's all you need to do. There's several other new terms that have been introduced over the years, like SIMU and DELU, and I do encourage that you read the manual to read about those. I like SIMU better than DELU, but sometimes either one works the same. It's just, I mean, one of the things that it's doing is it's taking advantage of the fact that if you have a long chain, the atoms at the end of the chain tend to be vibrating more than at the beginning of the chain. And so you can kind of allow it to more gradually change the thermal motion as you reach the end of the chain. And the program is very smart taking care of that. So EADP, let me go to that one. Another way to kind of manage things. So ADP stands for atomic displacement parameters. So E stands for equal atomic displacement parameters. You would use this, for example, when you have a mixed occupation site. You can use it when you have not only the same exact position for two atoms, but if you have two atoms very close to one another in a disordered model. Too close would be less than 0.5 angstroms in my experience. So, atom 1 and atom 2, if this distance from here to here is 0.5 or less angstroms, the thermal parameters are going to tend to be very unequal between the two. And I think that's an artifact. I don't think it necessarily should be the fact. So if you use EADP, make them equal, like say, suppose this is C1 and C10, you would just list them like this. And I believe that there's also an argument that you could put in here to constrain it at different values. But they will end up being exactly the same. It won't work if one of these is anisotropic and the other one is isotropic, though. It only works if they're both isotropic or both anisotropic. And then in the final res file, you'll see that they're actually equal atomic displacement parameters. It has its place. I've definitely used it from time to time. And a similar term is EXYZ. Like, you have two atoms on exactly the same site. You don't want them to fall away from each other. You want them to stay on top of each other. So you say EXYZ, equal XYZ, and then name the two atoms. Again, that would be a disorder situation, a mixed occupancy situation. So have a look at that PDF that I gave you that is now uploaded. It's so useful for remembering what these different commands mean. Fortunately, they often have a mnemonic. You kind of can guess what they mean, like EXYZ, equal XYZ. So it's not too hard to remember them. But there are quite a few, it's true. So the SHELX was really written about 1976, and there's been many, many versions since then. With each version, there's new features, and so I have the advantage of having used it from the beginning, from day one, and I only had to know, a limited number of commands, and now there's more and more and more and more. It always makes it more difficult. Yeah. So there's a lot of tricks, and fortunately, some of the software will help you out with that. Has anybody ever looked at SHELX, that program that I mentioned? It's called, I think it's spelled, this is a capital X and then an LE after it. I've only looked at it a little bit, but I've been impressed with its ability to model like frags and update the weight for you and check that your unit statement is correct. It's very helpful, very, very helpful. It's more up to date really than WinGX. Don't tell Sankar I said that, but it's more modern, I think. Yeah, it'd be something to try. It's free. You can see if you like it. And I thought the graphics were pretty decent too. I was going to use it in the class, but I didn't have enough time to actually get good at it, so I thought I better not, because I'll just waste your time. The other problem with this laptop, which is completely off the topic, but the resolution is so high that all the menu items in the program are just tiny, tiny, tiny. I could barely see them. So I don't like this laptop. Yes. Say it again. A which failure? A what? Hirschfeld. Hirschfeld. Got it. Okay, Hirschfeld, yeah. Yeah, so Hirschfeld was the first one to publish a paper describing the issue of the thermal ellipsoids being pointed at each other too much instead of being mutually perpendicular, which is the way they should be. Let's just look at a bond, like, again, CCl. And then there's something else out here. But this is a terminal chlorine. But you expect that this thermal ellipsoid will be like this one, and this one will be a little bit smaller. So this one is wagging a little bit more than this one, but they're both wagging perpendicular to the bond. And that's the complaint. If the Hirschfeld thing is bad, then the thermal ellipsoids are pointing more towards each other. Now, in my experience, that complaint is only because in a lot of cases you have a metal atom, and the metal atom has more electron density that's due to the bonding electrons, like d electrons, and those are going to make the thermal ellipsoid a little funny, especially if it's a heavy metal atom. So the bad Hirschfeld thing is often just because you have a heavy metal, silver, gold, mercury, or bromine. Yeah, it's just electron density around the atom that's causing it. It's not real. And especially if you have a double bond, also, a double bond is going to make the Hirschfeld thing look funny, right? Because you're going to have a lot of electron density between the two atoms. So sure, the thermal ellipsoid is going to be looking that way because of the double bond. To avoid it? It's not a fatal issue. I think it's just sort of a warning. So when you run the SIF check, there's alert A, B, C, D, E, F, G. At least goes to G, yeah. It's usually not an alert A or B. It's usually down further. If it's extreme, well, maybe you have the wrong atom type. That's possible. You have the wrong atom type. What else can you do except to make it isotropic? But that's going to really raise your R value if it's a heavy metal. Something with a lot of electrons is really dominating your scattering and really is the main thing affecting the R value. So, yeah, we'll talk about how do you respond to these alerts. You're probably a little shy because you think, I don't know why I have that. And sometimes you don't know why you have that. So you just have to say something that makes it sound like, I thought about it, but I don't know. Just to say to the referees, I did notice it, but I don't have an explanation. It doesn't make chemical sense, something like that, right? But it is good to point out that you've noticed it. What else can you do? Some things just don't go away. But sometimes it's good advice, so it's good to read it. And even the G alerts are sometimes good advice. A G alert may say, this space group could possibly be blah to a 93% probability, or percent, or something like that. 93%, I would consider that maybe the space group is wrong. But it might only be a G alert. So the SIF checker is powerful, but also kind of discouraging sometimes. Like I said, I think I've only had maybe 1 in 100 structures that says, congratulations, you have no alerts. Yeah. Yes. Say it again. Right. To get HKLF5, there's 2 ways. One is to collect the data and treat it as a twin, in which case you need 2 orientation matrices. And both of those matrices will be used to define the spots. And then ultimately that gives you the batches. Okay? So you'll have, say, 2 components, batch 1, batch 2. The output usually gives you a choice of having just HKLF4 or both HKLF4 and HKLF5. And the normal procedure would be to solve the structure with HKLF4, but refine the structure with HKLF5, in which case you put in that, and then you don't have a twin statement at all, but you have a BASF statement. The other way is to just go ahead and collect the data and treat it normally. Don't even worry about HKLF5 until you're finished, and then go into the program Platon, ask it to find a twin law. If it finds a twin law, it gives you an option to output an HKLF5 file. And then you refine using the HKLF5 file. And occasionally, that's a miracle. Sometimes it works beautifully, because Platon's smart enough to decompose these composite spots. In a way, it's cheating, but in a way, it also works. So that's another time when you might use it. Yeah. Usually, though, for solving the structure, you're better off just using HKLF4, final refinement HKLF5. So those are the only 2 ways I know how to generate it, either at the data reduction stage or with Platon. How many of you have ever looked at Platon before? Yes? So a few, okay. I have a problem again with this computer that the little icons are very small in that program. So maybe I'll borrow my husband's computer when we do that. It doesn't have that problem. Okay, so let's see. We have Wednesday and Thursday and half of Friday. So 5 more classes. Would you like to spend like a couple of lectures on SIF? Because it's such a big issue. Okay. And maybe 1 on graphics. How experienced are you with the databases? How many of you use CSD, Cambridge Structural Database? A few. Yeah, so not everybody has. Maybe we should spend a little time on the databases, particularly CSD. I use it quite a bit. And we have a site license at Davis, but I think we pay a lot of money, like $1,500 a year or something. But so many people use it, it's worthwhile. Everybody uses it. And once you have the site license, you can put it on all 5 of your computers, or however many computers you have. And that's really nice, too. So, but it has nearly 1 million structures archived, almost 1 million, imagine that. The vast majority of them since maybe 1995. And then everything just kind of exploded after that with the development of area detectors and fast computing and more people doing crystallography. So but it's very well written. It's very, very good. So again, it's Cambridge. It's based in England. They call themselves a non-profit organization. I guess they are, but we still pay a lot for the software. Yeah. Okay, so we'll do that and some more refinement stuff. And if there's something else you really want to do, let me know. Obviously, we can't cover the whole field in this limited time that we have. It's useful if you have somebody experienced in your lab who can help you, on a one-on-one basis sometimes. But, classroom situation isn't the greatest for that. So, let's go get some coffee, okay? Yeah.